The universe is full of surprises, which is why scientists and astronomers are always intrigued when a new discovery surfaces. Such discoveries sometimes provide answers to unsolved phenomena. However, some discoveries complicate the situation even more. One similar incident happened recently when scientists discovered a supermassive black hole. This black hole holds many mysteries and breaks several modern theories that scientists and astronomers have followed and believed in for years. What was found inside this supermassive black hole? Is it powerful enough to consume the entire universe? Join us as we explore how scientists just discovered a black hole that breaks modern theories. A black hole is an area in the final frontier where gravitational pull is so intense even light cannot escape beyond a certain region. This gravity tug happens because matter is squeezed into a tiny space, making it very dense to the point that it creates deep gravity sinks. These attributes make it one of the prominent landmarks in space, as anything that moves too close, either a star, spacecraft, or planet, will be stretched and compressed like cement. This process is what is known as a theoretical process known as spaghettification. The power of these black holes can be severely underestimated, which is why scientists and astronomers always keep watch on their activity and are always in search of new ones as well. A new distant supermassive black hole was discovered quite all right. Still, the violent outflow spotted from this supermassive black hole shocked scientists, and it is one of the most powerful outbursts ever seen from such an object. Astronomers have been observing this far-off, distant feeding black hole as it has been emitting enormous levels of energy and blowing large cosmic bubbles in its surrounding material. The discovery of this black hole started with the observations of a galactic cluster named MS-0735. MS-0735 can be found in the constellation Camelopardalis, and it is situated 2.6 billion light-years away from our planet. This region in space was observed because mysterious cavities, also known as radio bubbles, were found surrounding the black hole. As a result, scientists began to observe the black hole to figure out why they do not collapse like a deflated balloon under pressure from its surroundings. This phenomenon gathered a lot of attention that led scientists to divert their attention to this new discovery. Afterward, a research team was gathered to properly study the phenomenon, with McGill University physicist Jack Orlowski-Schirera being the lead author. From their studies, the research lead author announced that this phenomenon is one of the most energetic outbursts ever seen from a supermassive black hole. He also proposed further that this occurrence occurs when a black hole is being fed and fiercely burps out a massive amount of energy. Supermassive black holes are located in the middle of the biggest galaxies, including the Milky Way, which houses the supermassive black hole Sagittarius A star at its center. These home galaxies and their supermassive black hole inhabitants are mostly found together in groups of hundreds and at times thousands. Such gatherings of hundreds or thousands are referred to as galactic clusters. The clusters also house atmospheres that occupy the space between galaxies with hot gas or plasma, as great as almost 90 million degrees Fahrenheit, an equivalent of 50 million degrees Celsius. Though this plasma can cool over time and permit cold, dense gas to form and ultimately collapse to bring about new stars, and feed black holes that can work against this process. Supermassive black holes can reboil this gas repeatedly through violent outbursts of material. These outflows occur when some of the matter is blown out at a rate close to the speed of light. This process, known as feedback, quenches the new star's formation with the jets of material, also sculpting out cavities in the surrounding gas. As this gas is pushed away from the galactic cluster's center, it is restored by bubbles that beam out radio waves. The positioning of these huge volumes of gas needs a large amount of energy in turn. Astronomers have been trying to understand where this energy comes from and discovering what remains in these evacuated cavities. To discover more about such gas bubbles in galactic clusters and the procedures that birth them, a team of astronomers including Orlowski-Schirera tutored the Green Bank Telescope's Mustang II receiver on the cluster MS-0735. The Green Bank Telescope observations were accompanied by X-ray data collected formerly from MS-0735 by NASA's Chandra X-ray Observatory. They also engaged in a delicate distortion effect that swiftly moving electrons in the hot cluster gas have on the cosmic microwave background, a field of radiation left over from an event shortly after the Big Bang that equally fills the universe. The result of this fossil radiation was released 380,000 years after the universe's inception, when the cosmos had stretched and cooled enough to permit electrons to bond with protons, establishing the first atoms. This also allowed photons to move freely and create the first light, which is called the Sunyaev-Zeldovich SZ effect. Mustang 2 directs its observations at 90 GHz, a frequency at which the SZ effect signal illustrates mainly thermal pressure. With the power of Mustang 2, we are able to observe these cavities and start to observe accurately what they are filled with and why they don't crumble under pressure, said a research collaborator and European Southern Observatory astronomer. The team had determined that at least a piece of the support that averts cavities from disintegrating comes from things other than heat, with these non-thermal sources including particles traveling at near light speed, fast-charged particles called cosmic rays, and turbulence. They also discovered that a small contribution emerges from magnetic fields. This postulates that by mixing thermal and non-thermal sources, pressure support inside radio bubbles around supermassive black holes is more distinct than previously thought. The astronomers now look forward to observing the same system over several frequencies of electromagnetic radiation to notice just how exotic the black hole outflow is, and also receive a better insight into the physics of galactic clusters. These recent findings are the deepest, high-fidelity SZ imaging yet of the thermodynamic state of cavities in a galaxy cluster, Tracy Clark, the researcher co-author and U.S. Naval Research Laboratory astronomer, said. "We knew this was an exciting system when we observed the radio core and lobes at low frequencies, but we're only now starting to see the full picture. Now, these galaxy clusters are unique, but the mystery revolves around black holes. So how do they form? There are 4 black hole types: intermediate, stellar, supermassive, and miniature. The most widely known way a black hole forms is through stellar death. This happens when stars reach the end of their lives. At this point, some will inflate, lose their mass, and then cool before shaping like white dwarfs. But the biggest of these fiery bodies, those at least 10 to 20 times as large as our own sun, are fated to become either the so-called stellar mass black holes or super-dense neutron stars. In their last stages, massive stars would go out in large explosions known as supernovae. Such a burst throws star matter out into the final frontier, but leaves the stellar core behind. While the star was still alive, nuclear fusion generated a constant outward push that balanced the inward pull of gravity from the star's own mass. In the stellar remnants of a supernova, there are no longer forces to resist that gravity, making the star core start to collapse. A black hole is born if its mass caves into an infinitely small point. Gathering that much bulk, as much as the mass of our own sun, into such a tiny point would give black holes their immense gravitational pull. However, that doesn't make all black holes the same, as one black hole is not like the other. As predicted by Einstein's general theory of relativity, supermassive black holes can possess masses equivalent to billions of suns. These cosmic monsters are likely to hide at the centers of most galaxies. For example, the Milky Way hosts its own supermassive black hole at its center, known as Sagittarius A star, which is more than 4 million times as large as our sun. So far, the smallest members of the black hole family are theoretical. This small whirlwind of darkness may have spiraled to life soon after the universe formed with the Big Bang some 13.7 billion years ago, and then quickly vaporized. Astronomers also doubt that a class of objects called intermediate mass black holes survive in the universe, although proof of them is so far arguable. Regardless of their starting size, black holes can develop throughout their lives, consuming gas and dust from objects that move too close to the black hole. Anything that moves across the event horizon, the point at which escape becomes impossible, is in theory destined for spaghettification thanks to a sharp increase in gravity's strength as you fall into the black hole. As astrophysicist Neil deGrasse Tyson once explained, while you're getting stretched, you're getting squeezed, extruded through the fabric of space like toothpaste through a tube. However, black holes are precisely cosmic vacuum cleaners, as often portrayed in popular media. Objects must move pretty close to one black hole to lose this gravitational tug-of-war. For example, if a black hole of similar mass unexpectedly replaced our sun, our planetary family would continue to orbit undisturbed, however with much less warmth and illumination. Now, due to the fact that black holes swallow all light, scientists and astronomers can't see them immediately like they observe the sparkling cosmic objects in the sky. But there are a few keys that show a black hole's presence in a region of space. To start with, a black hole's powerful gravity pulls on any surrounding objects. Astronomers use these irregular movements to ascertain the presence of the invisible monster that hides nearby. Or objects can orbit a black hole. Scientists and astronomers can look for stars that seem to orbit nothing to observe a likely candidate. This process was how scientists and astronomers finally identified Sagittarius A's star as a black hole in the early 2000s. Black holes are also messy eaters, a flaw that betrays their locations and exposes them most times. As they swallow surrounding stars, their enormous gravitational and magnetic forces superheat the infalling gas and dust, making it beam out radiation. Some of this glowing matter covers the black hole in a spiraling region called an accretion disk. However, even the matter that starts falling into a black hole isn't necessarily going to stay there. Black holes can also sometimes push out infalling stardust in mighty radiation-laden bursts. The mystery behind these black holes is why scientists and astronomers are always observing the final frontier to watch their activities and watch out for new ones as well. Such observation was done recently, and analysis from the astronomers' observation done by scientists might just give hints that hundreds, if not thousands, of these stellar mass black holes may be hiding within our own Milky Way galaxy. In the new study, Charles Haley, an astrophysicist at Columbia University, and his colleagues surveyed data obtained and gathered by the Chandra X-ray Observatory over the years. When they observed the region of space within about 12 light-years of our galaxy's supermassive Sagittarius A star, they discovered hundreds of X-ray sources. The researchers then compared the X-ray emissions for those closest to Sagittarius A star with those a little farther away and saw huge differences. Haley gave examples for other scientists to see this phenomenon, starting with observing multiple X-ray sources within 3.3 light-years of the galaxy's core. These sources possess an irrationally high proportion of emissions at the highest energy wavelengths. By the way, present models of galactic evolution suggest that only one such source could be discovered that is close to Sagittarius A star. However, that theory got proved wrong as the team detected 12 instead. At least 6 of those X-ray sources, and possibly all 12, are to be what astronomers call X-ray binaries. Basically, one pair member is a garden variety star, while the other would either be a black hole or a neutron star. However, emissions from X-ray binaries that include neutron stars often gush unexpectedly and recede at least once every 5 to 10 years. Still, because the X-ray emissions from their sources haven't diversified in the past 12 years, Haley assumes that these binaries comprise small-mass black holes. This is a small number of sources, but they're very intriguing, says Fiona Harrison, an astrophysicist at the California Institute of Technology in Pasadena, who was not a part of the study. The balance of high-energy versus low-energy X-rays beamed out by these sources are consistent with those from low-mass binaries with black hole companions, she explained. In our neck of the galaxy, X-ray binary systems aren't seen often, but for every one such system astronomers have observed, they've also spotted many more black holes that don't have companions. Such isolated black holes would be too dim to distinguish at the galactic core, but the X-ray binaries stand as a tracer, proposing they're there and in very big numbers. Haley and his team concluded that even if only 6 of the X-ray sources include a black hole, there are likely between 300 and 500 solo black holes revolving within 3.3 light-years of the galactic core. This study may also help explain better how X-ray binaries form and grow. For example, in the crowded heart of a galaxy, black holes may have more chances to pair up with nearby stars and then sip material from them, generating X-rays in the process, than in scanty areas of the star group. But as of now, there's a lot of uncertainty about how these objects form. Let us know your thoughts in the comments section below.